Right.
So it's equal to 0 when d is -5, or d is equal to 1. So that's how we got the two d's.
Right.
And then we plugged into that equation for c.
Right. I just don't know how the problem knows that, like that's what we started with. Like, I don't.
All right, so we start out with a certain amount of momentum.
Right.
Just take any generic example. I got a 5 kilogram object going at 20 meters per second. If I asked you, give me a situation which has the exact same momentum. Well, here's one without doing much thinking. If I have a 5 kilogram mass going 20 meters per second, that will have the exact same momentum as this. Because it's that.
Yeah.
Same thing here. I have these two objects. There's a certain total kinetic energy, certain total momentum. Another situation which has the exact same total potential energy and kinetic energy. Sorry, try that again. Momentum and kinetic energy is that situation right there. So they're heading towards each other at that moment in time, and then the momentum and kinetic energy be the same at that moment in time, and then they collide. So the math is just trying to find the combination of C and D so that we get the exact same of what we started with.
Okay, that makes sense. Thank you.
And another solution, which is the one after they collide. So this gets rejected because this is pre-collision, or they somehow pass through each other. And I think that's sort of some of what you were going for. I was hoping, apparently your mind reading skills off today. But as these two objects are coming towards each other, you can assume that they're not going to go through each other. Now, this technique here does involve the quadratic. There's a lot more math in this technique, excuse me, than the other two techniques I'm about to do. However, the advantage of this is I'm feeling pretty good I did something right when I get my original situation as one of my solutions. The second technique, you just have to trust you didn't make a math error, but the math is simpler.
If you don't get the same like velocities as like if we didn't end up with the initial velocities as one
Then
of the
I
answers,
would assume we did make a mistake.
Okay, got you.
And I've been in situations in class where there's a Carol's error somewhere. I get to that point, I'm going, okay, there's a problem here. Let's figure out what the problem is. All right. Any questions at the moment? What is it?
Yeah, so I'm kind of like, so what exactly, like, are we solving, like, yeah, what are we solving for? Like,
The velocities of the two masses after the collision.
okay, so C is, so what are C and D? Like,
C and
is that
D
like-
are just my shorthand. It's the final velocity of 3 and the final velocity of the 3 kilogram mass and the final velocity of the 6 kilogram mass.
Okay.
I just use C and D because the more I write subscripts, the more apt I am to make an error. And so that's why I'm just using the shorthand.
Okay, now I'm just being sure.
Okay. I'm about to make another substitution. Why have you choose C and D for this is because I'm going to let capital A and capital B. Capital A is going to be the initial velocity of this, and B will be the initial velocity of the other one. Now, I did not write the vector symbol over those velocities, and hope you just sort of go with it. As opposed to my having to justify the mathematics by why I can justify doing that. All right. I'm going to start with this equation here. I'll get rid of that. I'm going to make this one more generic. Actually, I'll rewrite this one first in terms of A, B, C, and D. So I have 1/2. Actually, I'm just going to multiply by 2, get rid of my halves there. So this is m1a squared plus m2b squared is equal to m1c squared plus m2d squared. So just take a quick moment to verify that you understand what I did here, how I got this from this.
Do you not put 2 in front of anything?
I multiplied everything by 2, and that cancels all the 1/2 go away.
Okay. Oh yeah, cause there's a half in every, okay.
Yes, convenient. I'm gonna make my momentum equation a little bit more generic. So this becomes M1A plus M2B is equal to M1C plus M2D. So mass times velocity beforehand equals mass times velocity afterwards. I'm now gonna get all the M1 terms on one side, M2 terms on the other side for both equations. So for the momentum equation, I have M1A minus M1C is equal to M2B, I'm sorry, M2D minus M2B. And similar down there, M1A squared minus M1C squared equals M2D squared minus M2B squared. I'm now gonna factor. If I factor this one right here, I can factor M1 out, and I'm left with A squared minus C squared. I have a difference of perfect squares. How does that factor?
Isn't it just like A minus C?
We can't stop there. We shouldn't stop there. Pardon?
A minus C squared?
Oh,
Like
A minus
zero.
C, the whole thing squared?
Yeah.
No, definitely not. Difference of perfect squares.
A minus C, A plus.
A minus C, A plus C. If you FOIL, you get the A squared and the negative C squared. And then if you do the inner and outer, you get positive AC, negative AC, they cancel out.
Yeah.
And that's gonna be equal to M2 times D minus B, D plus B. I'm gonna take that top equation now, and I'm gonna factor that one. So the top equation, I get M1 times A minus C equals M2, and I'm gonna attempt to actually write letters the way I was taught. M1 A minus C equals M2 D minus B.
Why didn't you write the A plus C and the D plus B?
Factoring the first one, there's no squares in that.
Okay.
Other questions? Ben?
What are we trying to find right now?
What I'm doing is starting with the same initial conditions of kinetic energy being conserved and momentum being conserved, a way of solving these problems without having to use a quadratic. That's what I'm heading towards.
And we get the same thing?
Yes.
So we can like use any of them, either of them?
Yeah, I'm actually gonna show you 3 techniques.
So we're still finding the final velocities?
Yes. We know what the answer is, so we can check ourselves when we get there. I'm now gonna divide the left-hand sides, I'm gonna divide the right-hand sides. Again, the math people insist that as long as I divide by the same number on both sides, that's legitimate math, and so since those are equal, I'm doing that. M1 cancels out, A minus C cancels out, M2 cancels out, D minus B cancels out. I'm left with A plus C is equal to D plus B.
How
No.
did you know what to divide by? How did you know what to divide by?
Well, I've done this before, but also if I divided by this, it would cancel out 2 of the terms.
It would cancel out two, wait,
I canceled out the M1 and the, factors, canceled out two factors. M1's canceled out and the A minus C canceled out on that side, and then M2 and D minus B canceled out. So I'm just left with those.
but how did you know not to like cancel out A plus C and D plus B? 'Cause you could've-
Factor, because it has to be a whole thing, it's A minus C and A minus C.
Right,
I can't cancel out, I'm not canceling out A and canceling out C, I'm canceling out the whole
the
thing.
whole term, right? But,
Can you cancel like A plus C?
Can I
Yeah.
cancel that?
I'm just confused as to why you, like how you knew you didn't, how to not divide by A plus C and D plus B. Cause you could have canceled that out too.
Oh, A plus C I don't have any foundation to tell me that A plus C and D plus B are equal to each other. I do have a foundation that these are equal to each other from conservation of momentum.
Oh, okay, wait, so.
Because I started with this, got the M1 terms on one side, the M2 terms on the other side, and then factored it.
Okay, so that's like on the assumption that the velocities are the same.
No, the only assumption I have made for the denominators here is that momentum is conserved.
Okay.
The only assumption I've made for the top one is that it's a perfectly elastic collision and kinetic energy is conserved.
Okay. I think I kinda get it.
Alright, and then, was your question answered?
It's the same question. Was the same question.
Alright, do you feel like it was answered?
Yes.
I'll go with that. A lot of the times when I'm doing derivations like this one, it's so that you know where the stuff comes from as opposed to, hey, here's a formula that you can use. There's some legitimate physics behind it as opposed to like just making stuff up or textbooks making stuff up. So a more traditional way of writing this would be to put all the initial terms on one side and the finals on the other. A and B were my initial terms, so that would be A minus B is equal to D minus C. This is known as the relative, why am I blanking on the common terminology? Speed of approach, relative speed of approach, there we go. Relative speed of approach. In other words, how fast is A coming towards B? So if you're standing in B's point of view, how fast is A coming at you? The other one is the relative speed of recession. So if you're standing in the 3 kilograms point of view, how fast is the 6 kilograms going away from you? Relative speed of recession. All the letters are there in one form or another. So let's see what that gives us. We had negative 18, because we've already solved it. Negative 18 is equal to 3c plus 6d. In this case, we can divide by 3, and it simplifies down into negative 6 is equal to c plus 2d. From the equation that we just derived, a minus b equals d minus c, that would be 4 minus negative 5 is equal to d minus c. Two equations, two unknowns. So from this one, it doesn't matter which one we solve for, let's solve for c. C is equal to d minus 9. If I plug that into the first equation, I get negative 6 is equal to d minus 9 plus 2d. So if I add 9 to both sides, I get 3 is equal to 3d, d is equal to 1. I was about to circle, oh, there it is, right there. Boom. Which is what we had last time. C is equal to D minus 9, and 1 minus 9 is negative 8. Obviously, the advantage of this is the math is simpler once you know this, and you can pair it up with conservation of momentum, no quadratic involved.
If we were to use this method, do we need to derive and show this relationship, or could we just use those?
You can just use it.
So we know that A minus B is that relative speed of approach, and B minus C is the relative speed of recession. Is that what we use to find, like, what C and D are equal to?
That's one of the equations. So since I have two unknowns here, the velocities afterwards, I have to have two equations. And so the first equation is still conservation of momentum, just like before. The second equation, you can use this, or either form of it. You can use this instead of writing out the full kinetic energy one that we had.
I'm pretty sure Anna just asked this, but that's like a general, like, we can use that for every problem?
Every one-dimensional perfectly elastic collision,
Okay,
there are some restrictions.
gotcha.
Some restrictions apply.
Wait, which one did we end up using? Is it the A plus B, A plus C equals D plus B, or was it the subtraction one?
That, I used that version right there when I created that equation right there.
Okay.
All right, here's a question for you. When we went through it the first time, we had two solutions. We had the answer to after the collision, and then we had the before collision solution. When we did the second technique, this did not show up. What point did we lose this solution?
When we did the derivation, because this is assuming, like, the
Right.
relative speed of approach, and it's like before and after.
Right, but where in the derivation did that solution go away?
Where we
It's
cancel.
like D minus B and A minus C. Like when we cancel that out.
Like,
Where you're
Wait.
dividing,
at this point,
yeah,
why did it go away?
because you canceled out A minus C and.
Oh, that's not the point at which,
Okay.
because that would make it sound like canceling out doesn't always work.
It's kind of what I was gonna say, I don't know.
Does it have to do with the, like, squared up here?
No, not at that point. You're actually, you and Jacob were in the right area. Yes.
So back down here.
I did make a comment about what the math people insist upon, and I did leave part of that out.
Is it about dividing from both sides?
When can you not divide both sides by the same thing?
When they're not the same thing.
Never
Never
mind.
mind.
There is an exception to when dividing by both sides by the same thing is forbidden.
When it's 0?
Remember, A is beforehand, C is afterwards for this 3 kilogram mass. If they are equal, in other words, the pre-collision solution, if they are equal, then A minus C equals 0. Similarly, D minus B is equal to 0. So when I divide it by A minus C and D minus B, that only works if it's not equal to 0. And that's the point when the pre-collision solution
So
disappeared.
how do we know to look out for that?
I mean, it's already built into it.
Okay.
So if you do the second technique, easier math in my opinion, but just recognize you're not gonna get that automatic check right there at the end.
You're assuming that they're not the same. The velocities are different.
Yes, they have to be different.
Right, okay. would you end up with 0 at the very end if they were the same?
Now, you can set up a situation where their speeds are the same before and afterwards, but not the velocities. So, there's no way you're gonna have two objects that actually collide, interact with each other in a one-dimensional collision, and then we'll end up, actually, any dimensional collision, where they actually collide and they end up with
Different speed.
the exact same velocity they started with. The only way that happens is
Pass
that
right
they,
through.
as Ian gestured also, is that if they pass through each other,
Okay.
which does not happen in classical physics. Quantum mechanics, it might happen, but not here.
Okay.
Quantum mechanics is what gives us hope to be able to walk through walls.
Yeah. It just has to happen for all of the atoms at the same time.
Yeah. And hope that the wave function doesn't collapse halfway through the wall. All right, technique number 3, which is actually the technique that I like. I find it the simplest of all the maths, but it's slightly more abstract. So I'm going to start out with, this thing's going at 4 meters per second. This is what I'm calling the problem frame, or sometimes just referred to as the lab frame. And so we're all standing here, we consider ourselves at rest, and that thing is moving along at 4 meters per second based upon our point of view. What would happen if I'm moving 4 meters per second to the right? How fast would this seem to be going?
0.
How fast would that seem to be going?
Faster.
9 meters per second?
Sorry?
9 meters per second, Philip?
And the velocity?
That's right.
Like in the negative direction.
Yeah,
Yeah.
-9.
Oh, I said to the left.
Oh, okay, oh, sorry, missed it. So if I take whatever the velocity that is, so we had A and B, and just subtract what my velocity is. So subtract velocity of the observer. I have what the velocities are in a different reference frame, from a different point of view.